So this is digital image processing, and we are dealing with the image enhancement using frequency domain or filtering using frequency domain. Under that, we will discuss the topic of discrete Fourier transform. First, we'll take up the one-dimensional DFTs and how we can compute that, and how the DFTs are used for computing the so to say circular convolution as well as linear convolution is what we will see. And further, we will try to go for the two-dimensional Fourier transforms and how they are related to the one-dimensional DFT. And then, if time permits, we'll go for the Moire patterns. But otherwise, we'll take that up in the next class. Okay, so discrete Fourier transform. Please do not, turn on your audio or something like that, video or anything like that, because that will be a disturbance in the recording also. So the DFT, pair for a signal of Fn of length n can be written something like this. This is, Fk, which is found using the DFT. This is known as DFT, and this is known as inverse DFT. So Fk is equal to sigma of n equal to 0 to n minus 1, Fn e to the power of minus j 2 pi nk by n. And that is the DFT, and the inverse DFT is Fn is equal to 1 by n sigma n equal to 0, n minus 1, Fk e to the power of j 2 pi nk by n for 0 less than n minus 1. So these two form a DFT pair. Okay. Also, the DFT of length n signal is periodic with period n. We see that it is periodic with period n, and we write it as f of k plus n equal to f of k. F of k plus n is equal to f of k because it is periodic. This is due to the periodicity of the complex exponential, and the complex exponential is written something like this: wn to the power of small n, and wn is e to the power of j 2 pi n to the power n. So this e to the power of j 2 pi n is already there in our expression, or rather wn to the power n, which is e to the power of minus j 2 pi n by n, is already there in our expression, which is over here, right? So this quantity, which is e to the power of minus j to the power of n by to the power of pi by n, is known as the w suffix capital N. Okay, w suffix capital N is this quantity, and the when we write plus over here, this is minus and this is plus, then this becomes w to the power of w suffix n to the power of minus 1. Okay, so we can try to write that, and we have the property that sum of the complex exponentials, which is 1 by n sigma n equal to 0 to n wn to the power kn is equal to 1 for k equal to rn. So this just gives you the periodicity. K is equal to rn will give you rn, all r small n capital N, wn wn to the power capital N will give you the value 1. But if k is not equal to rn, then it turns out to be 0. So this is sum of the exponential. This is the standard property. The proof is left as an exercise. You can just try to substitute that and try to write it 1 by n sigma n equal to 0 to n wn to the power of, in place of this k over here, you can substitute rn, and wn to the power n will be just, e to the power of minus j 2 pi. E to the power of minus j 2 pi is, cos of 2 pi minus j sine 2 pi. Cos of 2 pi is 1 and sine 2 pi will be 0. Okay, sine 2 pi is 0, cos of 2 pi will be 1. So therefore, that quantity will be 1. If k takes any other value other than, rn, say for example, r of n minus 1, okay, then that will give you in the rotation the value equal to 0. Okay, because it will be around the circle. So this will be, when we try to write this, this will be a angle around the circle. So the DFT pair of signal Fn of length n may be expressed in the matrix vector form. We can replace that e to the power of minus j 2 pi by capital N as the W suffix of N, and here W suffix of N with a minus to the power, where Wn is this quantity over here. Now, this can be written in the matrix form also, by this. F is equal to AF, where A is nothing but Wn to the power 0, 0, Wn to the power 0 to the power 1, and so on, right? We can keep on writing this, and this will be Wn to the power n minus 1 whole to the power n minus 1. Now, depending upon the values of K can take values 0 to n minus 1. K can take value 0 to. So for f of 0, we will get for capital F of 0, we will get the first row, right? For capital F of 1 over here, when K is equal to 1, we will get capital F of 1, and that corresponds to the second row over here, right? And when capital K is equal to 2, then we'll have capital F of 2. K is equal to 2, then we'll have F of capital F of 2, and that will correspond to the third row. Similarly, when so to say, when K corresponds to capital N minus 1, F of capital N minus 1 will be corresponding to the row which is there over here. And this row A is multiplied by F, and F is nothing but this quantity F of 0, F of 1, F of N minus 1 to the power transpose. Transpose means it will become this is a, so to say, after taking the transpose, this becomes a column matrix. This becomes a column matrix. This also is a column matrix where F is written F of 0, F of 1, F of 2 till F of n minus 1, right? So this is nothing but, so to say, n rows and one column, n cross 1. And this will be n into 1, and this will be again n cross 1. So n cross n multiplied by n cross 1 will give n cross 1 matrix, which is same thing as this. Now, see the computation of this, all these values, this is 1, this is also 1, this is also 1, this is also 1, because anything to the power of 0 is 1, and 1 to the power anything will be 1 itself. Okay, anything to the power of 0 is 1, and 1 to the power of anything is 1 itself. Similarly, here we might have, anything over here, but to the power we have 0. So all these, this column also, first column and first row, we will have all ones. Other things, it depends upon the values, so many other values. So depending upon the value of capital N, so you can see when the value of capital N is 4, then first row and first column definitely are ones. The other values will be, you just need to substitute there and get the value. Okay, you need to substitute there and get the value. So this will be Wn to the power 1 n. So W4 1 to the power 1. So that will be e to the power of minus j 2 pi by 4. E to the power of minus j 2 pi by 4. So 2 pi by 4 will be, pi by 2, and pi by 2 is nothing but 90 degrees. So e to the power of minus j pi by 2 will be cos of pi by 2 minus j sine pi by 2. So cos of pi by 2 is 0, and sine pi by 2 is 1, and therefore that term will become minus j. So that's how you can get this value as minus j, right? You can get this value as minus j. Similarly, you can go back over here and see this is Wn to the power 1, that is W4 to the power 1 whole square. So that will give us e to the power of minus j 2 pi by 4 into 2, and that will give e to the power of minus j, 2 pi by 4 into 2, that will give us e to the power of minus j. E to the power of minus j will be cos of minus pi minus of j sine pi. Cos of pi minus j sine pi, that will be the value. And cos of pi will be the value which is 1, and the sign of pi will be 0. So therefore, that quantity might turn out to be 1 with a minus sign, of course. The cos of pi will be, sorry, minus 1. Cos of pi is minus 1, not plus 1. Cos of 0 is 1. Cos of 2 pi is 1. Cos of pi is minus 1. Okay. Similarly, you can try to find the last value over here. That is when n is equal to 4, you will have 4 by 4 matrix, and therefore it will be Wn W4 to the power 1 whole cube. Okay, Wn to the power 1 whole cube will be Wn W4 to the power cube, and that will give us e to the power of minus j, 3 pi by 2. Okay, 3 pi by 2. And hence that will just turn out to be the value. Okay. Similarly, you can calculate all the other values over here. You can calculate all the other values over here. So the inverse DFT is then expressed by the, so-called small f is equal to A inverse of F. F is equal to capital F is equal to capital A into small f. So small f will be equal to capital A inverse into capital F, where A inverse is nothing but, should first take the complex conjugate and then take the transpose and then divide by n. Okay, A star whole to the power n, whole to the power t divided by n. So this is nothing but A star transpose by n. So 1 by n, and you can try to write this term. This is just complex conjugate and then the transpose. So this is derived by complex exponential sum property. Now let us see what linear convolution corresponds to in the time domain. So if we have f of n equal to 1 to 2, h of n equal to 1 and minus 1, then the size of fn will be 3, therefore n1 is 3 here. Size of hn is 2, therefore n2 is equal to 2. So the length of the convolution of fn with hn, which we call it as gn, will be nothing but n1 plus n2 minus 1. That is 3 plus 2 minus 1, that will be 4. And that is formula for that is written here, m equal to minus infinity infinity, f of m, h of n minus 1. So f of first might be, you should keep on multiplying. Middle term, when m is equal to 0, will give us f of 0, h of n. Then when m is equal to minus 1, it will be f of minus 1, h of n plus 1. When n is equal to plus 1, then we will, m is equal to plus 1, then we will have f of plus 1, h of n minus 1, and so on. So we can write an m equal to 0 term first, and then we can write the terms on both the sides. Keep on writing like that. But what appears over here is, when we try to write all that, then we will write here n equal to 0, n equal to 1, n equal to 2, n equal to 3. 4 different terms, n plus n2, n plus n1 plus n2 minus 1 will give you the term value 4, and therefore n is equal to 0 to 3. 4 values will have. So when n is equal to 0, then the f of m value is written over here, 1, 2, 2. So this is f of 0, this is f of 0, f of 1, f of 2. This is f of 0, f of 1, f of 2. This is h of 0, and this is h of 1, right? So therefore f of 1 is written, f of 0 is written here, f of 1 is written here, f of 2 is written over here. Now when n is equal to 0, we will have h of 0 minus m, 0 minus m. Okay, so when we talk about 0 minus m, so we will have h of minus m, h of minus m. H of minus m is what we have over here. When n is equal to 0, h of n minus m will become h of 0 minus m. So h of n is 1 minus 1. So h of minus m will be what? H of n is 1 minus 1. 1 and minus 1. So h of minus m will be, we need to remember that this is at n equal to 0 and this is at n is equal to 1. But because of this minus term over here, this value will remain at 0, whereas this value will, in this case, will go to, -1. And -1 is the term which is, here. This is corresponding to f of 0, 1, 2. Okay, f of 0, 1, 2, we have the values 1, 2, 2. This will be the value which is corresponding to m equal to -1. And therefore, that entry will be there here and that entry will be there here. Now, when n is equal to 1, we will have h of 1 minus m. Now, this is just a shifted version of this by, 1 unit to the front. Okay, this is just a shifted version of this 1 unit to the front. That is, this is moved front 1 unit. Then when n is equal to 2, we will have h of n 2 minus m, which is again 1 unit, shifted to the front of this value. So that means this is shifted by the 1 unit over here. Similarly, 3 minus 1 is again further 1 more shift. So now what you need to do is you need to multiply f of 0 with h of 0, f of 1 with h of 1, f of 2 with, convolve that. So that just means that you need to multiply, corresponding values and add. So here, to get the value corresponding to n equal to 0, that is f of 0 star h of 0, we write here f of 0, h of n. Okay, for that, what we try to do is, this is the quantity here for f of m is 0. So 0 into -1 will be 0. So there's nothing there here. Therefore, we'll get nothing. This is 0, 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 this is 0. So therefore, we'll get first term only 1 into 1. Okay, this is just 1 into 1, and that will be 1 over here. When we multiply this with this, then we'll get 1 into -1, that is -1, plus 2 into +1, that will be 2. So -1 plus 2 will give you again a value which is 1. Now, if you want to multiply this with this, then this 2, 2, which should be multiplied with this -1, 1. This 2, 2 should be multiplied with this -1, 1. So 2 into -1 plus 2 into 1 will give us the value which is 0. Next, this should be multiplied with this. That means this quantity and this quantity only should be multiplied. 2 into -1 will be -2. So corresponding elements are multiplied. So hence we'll get the Gn value like this. And that is Gn is equal to 1, 1, 0, -2. Okay, this is the linear convolution method. Now, same linear convolution, how we can get using DFTs is what we'll see later. So that was linear convolution. Then we also have what is known as circular shift and correspondingly circular convolution. Signal n of length n, if we have a circular shift, ensures that the resulting signal will keep its length n. So if we have a circular shift, this ensures that the resulting signal will keep its length n. That means it comes back to the original position. And that we denote by shift mod n. Okay, circular shift is denoted by shift modulo n. And that is written as, mod n. Okay, it is a shift mod n denoted by the mod n over here, x of n minus m, with the period as capital N will be x of n minus m mod n. So example of this is, we can take x of -2 to the, so to say, when capital N is equal to 8. That will give us the same thing as 8 minus 2 or -2 plus 8. -2 plus 8. So -2 plus 8 will give us the value 6 over here. Similarly, the value here, you can just try to write anything over here. This is written as, mod n means you can subtract by 8 or add by 8 or, subtract by 2 into 8 or add by 2 into 8 and so on. Then 3 into 8, 4 into 8, all that follow. So the convenient values are x0 to x7. When n is equal to 8, then we just write values which are x0 to x7. So all of them, we try to bring it into that level. So -2 means -2 plus 8 will give us 6. 10 means 10 minus 8. That will give us 2 and so on. Say if it is 20, 20 minus 2 into 8, that will give us 4. If it is minus 20, then minus 20 plus 2 into 8, that will give minus 4, but minus 4 again does not have any meaning. X0 to X7 is what we want. So minus 4 plus 8 again will give us the value which is plus 4. So thus we can bring all these values within a particular range. So the circular convolution of this can be considered, with this 1, 2, 2, 1 minus 1, n1 equal to 3, n2 equal to 2. Then circular convolution symbol is written like this, and we write here the modulo n, or circular shift modulo n, capital N. But the result, the length of the result, okay, the length of the result, or the result is of length n, where we'll have max of n1 comma n2. Earlier it was n1 plus n2 minus 1 for linear, but for circular the resultant also will have n1 comma n2 equal to 3. Okay, n1 plus comma n2 equal to 3, and that is equal to 3 only here. One is having 3 and another is having 2, so 3 comma 2 equal to 3. So for that, circular convolution, this one minus 1 is going to go to this position. Okay, this value is going to go to this position. So because this is, the quantity which is corresponding to, minus 1. This is corresponding to the minus 1. So minus 1 should go to 2, because the value of n is equal to 3 now. So the corresponding, shift will be, circular shift will correspond to this being shifted to this position. So now if you want to multiply this with this, corresponding values of this should be multiplied and added and get this. Then corresponding value this with this, and this with this, and this with 0 to be multiplied and added, you'll get this. Corresponding value this with 0, and this value with this y minus 1, and this value with this to be multiplied and added to get the resultant 0. So thus we will get the Gn like this. The Gn like this. So that's how we'll get the circular convolution by means of writing the proper, symbolic way. So this symbol is for, circular convolution, and for normal convolution, we just write the asterisk. So generally we see that there is a relationship between the circular convolution and the DFT. So DFT is also circular, and so circular convolution in the time domain is nothing but multiplication of the DFT. So if Gn is equal to Fn circular convolution h of n, then that is equivalent to G of k equal to f of k into h of k. So convolution, circular convolution in the in digital domain, n domain, will be same thing as the what you call multiplication in the frequency domain, so to say, over here. This is spatial domain, and this is the frequency domain. So circular convolution in the spatial domain is nothing but multiplication in the frequency domain. So the property holds for circular convolution, but not for linear convolution. So in signal processing, we are interested in linear convolution, not in circular convolution. So do we have a similar property for linear convolution? Yes, we can extend this circular convolution to correspond to linear convolution by what is known as zero padding. Okay, by zero padding. So what we do is we take, we have written this already. So if Fn is of length n1 and Hn is of length n2, then Gn is equal to Fn star Hn is of length n1 plus n2 minus 1. Okay, n1 plus n2 minus 1. So if this is the length there, how much extra is corresponding to this? That is n2 minus 1. And how much it is corresponding extra corresponding to this, value of n2. Okay, that is n1 minus 1. That many zero padding should be done. If the signal are zero padded to length n equal to n1.
Yeah.
So we have here the zero padding. Zero padding should be done so that the length of both Fn and Hn are made equal to N1 plus N2 minus 1. That many zeros should be added to it. Then we can take the circular convolution. Then the circular convolution will be same thing as the linear convolution of the earlier one. So we'll get here Fn and Hn with zero padding, Fn and Hn with zero padded signals compared to Fn and Hn, and then whatever convolution of that is there, that corresponds to the Gn. And corresponding to this, if you multiply the two DFTs of these two terms, then you can just get the what you call so to say DFT of the Gn. So if you try to do that, we'll get this. So we are doing the, what you call zero padding. Say if n is equal to n1 equal to 3 and n2 equal to 0, n2 equal to 2, then the value of n is equal to 4. So you need to add 1 0 to this, and you need to add 2 zeros to this. 1 0 to this and 2. So Fn will be 1 2 2 0. Only 1 0 is added to Fn. Whereas to Hn, we are adding two zeros, 1 minus 1 0 0. 1 minus 1 0 0. Now this dash here indicates that this corresponds to n equal to 0. This indicates that this is at n equal to 0. This is at n equal to 0. So naturally this is at n equal to 1. This is n equal to 2. This is n equal to 3. This is at n equal to minus 1, 2 and 3, right? H of 0 is this, H of 1 is this, H of 2 is this, H of 3 is this. Similarly, F0, F1, F2, F3. So now having written this, we can write 1, 2, 2, 0 over here, and then this value of 1 minus 1, 0, 0 is to be written at, a place. 1 minus 1, 0, 0 is to be written at a place. Correspondingly, you can try to write this quantity, h of n minus 0, 4, h of n minus 1, 4, h of n minus 2, 4, and h of n minus 3, 4, right? So this quantity, or rather whatever we have here is there here in the reverse order, right? In the reverse order is there over here, and all these are just shifted versions of these. So if you see this, we are writing this over here. If you shift it once, this minus 1 will come over here, this 1 will go there, this 0 will come here, this 0 will come there. Again, you shift the whole thing once, this 0 will come here, this minus 1, this 1, this 0. Similarly, if you shift this once over here, this 0 will go there, and this 0 will come here, and this minus 1 will come here, this 1 will come here. So each one of this is a shifted quantity compared to the above one. Okay, so this quantity, rather, we should have written here. This is not n. This is h of n is written here over here. If you want to write it in terms of h at, then it will be h of so to say, when we take the reverse of that, we will get the value 1 0 0 1. So this quantity is just you can say that it is so to say shifted, so to say twice shifted. Is it twice or no? I think it is inverted. It is just inverted and then shifted version of this. Now you need to multiply this with this corresponding quantities and then add, you'll get this. Corresponding quantities, multiply and then add, you'll get this. Corresponding quantities, this with this, this with this, this with this, this with this, and then add, you'll get 0, and so on. Okay, so this is the way we do the linear convolution. So we'll try to do